Hi, my name is, and I'm one of these. I work for this company, being one of these for them. I'm also one of these, although not the goblin kind. I'm more like one of these, although not the female cyborg kind. So I'm basically this guy. Can you see the guy? He's behind Spider-Man, and he comes with a fitting title. And it's a fitting title because, like many of you, I'm very good at doing this, but pretty terrible at doing that. However, I must be doing something right, because since COVID hit, I've had one of these bad boys running in my bedroom 24/7, and I haven't slept worse since. People also seem to think I am one of these, but I'm not that old. I'm more like one of these, although I'm not that edgy, so I'm more like one of these, although I look nothing like Rami Malek, which this guy does. But I must be one of these, because 2 years ago I entered this contest and won by writing this little article, which a lot of people thought was very suspicious for some reason. Recently, I've also written about getting this thing to work on that thing, how to make sure that this thing keeps working fast, which these guys must have really liked because I'm doing a talk on their sponsor track right now. So this is me, and as you can see, we look nothing alike. Really spent some time in the slides for this one. So yeah, that was my 90-second intro. And this is Primitive. Primitive is a free Mac app and command line tool that allows you to create these artsy-looking images built from primitive shapes, hence the name. In this case, they're tiny triangles. It's written in Go, so it's going to go fast, and we can actually watch it go fast in real time. As you can see, we're adding probably about 100 shapes by now, going on to 200. And if we give it some time, just close the window, and you lean back a bit, sort of squint your eyes, you can start to make out where this is going. More GIFs. Since the algorithm has a random component to it, we can run the same source image through the algorithm multiple times to create some cool looking artsy GIFs from static images like these crayons. And another cool little application are placeholder images. As the output image consists only of primitive shapes, we can use these tiny SVG files as placeholders using SourceSet for larger images on our website. Yeah, so these are the two side boosters landing. So I was intrigued and started wondering if it would be possible to create art like this from images in PHP. As the original project is open source, it should be possible to reverse engineer the code from their GitHub repository and get the algorithm like that. So that's what I did, and I built it in PHP, and of course it was terribly slow. So yeah, are we here just to suffer slow PHP code? No, we're here for lunch. On any other conference, this would be probably the worst time slot to have. I'm just hoping you're all chilling with a sandwich and coffee, and we can look at some art and algorithms. So as a start, we'll take a look at that algorithm we just saw. It's going to be very visual, no code yet. And then for the main course, we're actually going to build it in PHP and look at some code there. Finally, as it involves looping over thousands of pixels and hundreds of triangles, well, obviously we're going to have to look at optimizing the performance. And we'll do that using Blackfire. Very quickly going to jump back to here. All right, good. Looks like we're still live. You can still see the slides. So the first time I heard about algorithms was in the movie The Social Network. There's a cool scene where Andrew Garfield, on the slide here, writes a girl rating algorithm on a dorm room window. And back when I was 14, I remember thinking, well, shit, I got to get into Harvard now and learn all this math stuff if I want to do cool stuff and be the next Mark Zuckerberg. Well, I don't know why anyone want to be the next Mark Zuckerberg at this point, but my point remains the same. But it turns out that both me and the Zuck were wrong. According to Wikipedia, an algorithm is a plan, a set of step-by-step instructions to solve a problem. Turns out that they aren't exclusively complex math equations or math problems, and you definitely don't need to go to Harvard to understand them. So let's bring it back to our primitive algorithm, problems and steps to solve them. Well, the problem we're having is we have this image, and we want to turn it into this image. And the set of step-by-step instructions to do so looks like this. So you see there's only 7 of them, and it's really not that bad, so let's go over them. The first step would be to scale the target image. We do this because, well, the algorithm doesn't need every pixel in this 4K image to make up its mind about the triangles. In fact, we can basically scale it down to a 256 times 256 pixel canvas, or sort of put it in that boundary box. And that gives us more than enough pixels to work with. We're also going to call this resized image the target image, because it's the target we'll be working towards recreating. And you'll see that name, target image, popping up multiple times. The next thing we need to do is create a new empty image canvas. We'll call that one the current image canvas. And we'll make it the same size as our target image and give it a fill color, which is the average color of our target image. In this case, this lovely shade of blue. We'll call this a current image, as it's sort of our current work in progress. It's our canvas on which we'll be iteratively and incrementally like drawing triangles. And at the end of our loops, at the end of our algorithm, this current image is the one that's going to be the finished result. So right now it's terribly empty. We need some triangles. And you've all done this in primary school. Random triangles is easy. You start with 3 random points and you just connect the dots. Great, that's a triangle. Now we need 200 more. Or for demo purposes in this presentation, like 15 or 16. Well, we're not just applying them to the current image canvas yet, because these are not the 200 final triangles. In fact, they look nothing like the target image. They're just a great starting point. You can also see we've already given them a certain color, which is based on the average color of the underlying area on the target image. Now the next step would be to select the best shape. We do this by drawing each of these triangles on top of the current image, producing a new image, which we can then compare to the target image to produce a score. But let's look at that in a bit more detail, because that one sentence doesn't really explain it. So selecting the best shape. For example, if we take 2 random triangles out of our pile of 200 triangles, we can then overlay them on top of the target image, and we can clearly see that the second one has a better fit than the first one. It sort of really blends into that shoulder, while the first triangle sort of just clips into our face. So the question remains, how do we tell the program to make that decision? Well, this is where the math comes in. Now, I didn't take any advanced statistics classes, didn't go to Harvard either. I just looked at 2 hours of YouTube videos, so now I'm kind of an expert at this thing. Let me try to explain. In statistics, there's this thing called the root mean square deviation, or RMSD, or deviation for short. It's a value that measures a difference between a predicted value and an observed value, which probably tells you nothing. Its application, well, it has applications in statistics, machine learning, and image processing. So if we sort of change the definition, and since we're scoring images, we can basically say that the root square mean deviation, or deviation, is a value that measures the difference between our current image and the target image. Or even shorter, if that was all completely over your head, how different are these images? So we're calculating the root mean square deviation, or deviation, from our target image on the left here for our example images on the right. And as we can see, the first image from Keanu Reeves is a completely different image. So it's going to deviate a lot from the target image. It's going to get a score of 6. Higher is worse times lower is better. So the first example is clearly a different image, so bad deviation. The second image, or second example, is our triangle, and it's got that average color going for it. So the deviation value is going to be a bit lower. It's going to be 0.6. Finally, just for the example, the last example is the same image as a target image. Well, obviously the deviation is going to be 0 in this case, because they're the same image. They don't deviate at all. So back to triangles. Now we know why and how we're going to use that deviation value. We can now take each and every one of our triangles, apply it to the current image, calculate the root mean square deviation to our target image, which is 0.4 in this case, and repeat that whole process. Here's another triangle, and here's the values for, well, what is it, 12 triangles, but 200 in our real algorithm. And that clearly shows us that this shape is the best shape to continue with because it differs or deviates the least from the target image and thus brings us closer to it. So where were we? We've just selected the best shape using math. It's this one. And if we bring back the target image and sort of zoom in a bit, we can see that this triangle, the best triangle, has a pretty good match with that purple patch of hair. However, there's still some points sticking out into the blue background, and there's like a point sticking out into her face. So the fifth step is to optimize this. And we want to optimize this triangle to minimize the differences between the target image and this triangle. And we do this by mutating the shape and calculating its score after each mutation. It's a bit like nature mutates things to make things better. So we move a random point like this. We redraw the triangle, recalculate the score, and at this point it actually got worse. It went up from, what was it, 0.08 to 0.11, and the triangle is sticking out way more into the background. So we'll reset and try again. Move a point, redraw the triangle, recalculate the score, and this time we were successful. Its score got better, and it's clearly no longer sticking out into the background. So we can keep doing this multiple times, for better or for worse. This is worse, so back one step, retry, and we keep doing this for a number of times. Well, a limited number of times, actually, because this is called hill climbing. The only problem with hill climbing is that it's prone to get stuck in local minima, which is a complex and statistical way, again, to basically mean bad results. So that's why we're creating 200 triangles to start with, instead of starting from one triangle and hill climbing up from that point. So here's our winning optimized triangle. If we take away the border, we can see that it's really fitting into the target image really well. Like it's almost, I would say, completely invisible. Probably after screen compression, it's invisible. We can then apply this newfound triangle to our current image. So the current image at this point is still empty. It's a blue canvas on the right there, and our new triangle is applied on top. Finally, our first triangle is down, and we only need to repeat these how many times? These 4 steps 200 times for a recognizable yet artsy result. And that looks like this. It's pretty cool. You might notice that we're using semi-transparent shapes here, and that's just because they're a bit more forgiving and the resulting art piece looks a bit better. And yeah, I think we're probably up to about 200-ish shapes now. Yeah, it's starting to look pretty good. So let's talk about the elephant in the room. That was a theory, now we're going to practice. We're going to build this algorithm in PHP. We already know it works in Go. We already know some poor soul built it in JavaScript. So there's no real reason it shouldn't work in PHP. And in fact, we've had the tools to do so for years now. Introducing Imagic. In my opinion, the most underrated PHP extension out there. It's not only old, it's also not only used for converting images or scaling images, but it can also do way more things like drawing shapes, drawing text, doing filters, special effects, etc. Also, its documentation is way better than the PHP docs. It's got interactive examples and birds, so those are two pros. So let's get right to it. Without going through the entire code base, because that would be pretty intense for a lunch session, let's look at some key points. More specifically, let's look at the steps we took in our algorithm and look at how they look in PHP. We'll start with an easy one, scaling the target image. Well, these are really the Imagic basics. We're creating a new Imagic object, we're loading image.jpg into it, and then we're calling Imagic's native scale image method to scale it down to 256 times 256 boundary box. This is, we've seen this in the steps before. We're also adding the fit parameter to make sure it doesn't mess up our aspect ratio of our original image. So that was pretty easy. Just going to grab a quick sip. The next step would be to create that empty current image canvas. That was sort of our work in progress canvas. And again, here's that code from before. and we'll add some code to create a new imaging instance. But now we're not loading a file, we're just creating a new image. And this new image is going to have the target image's width and height. And we're also going to fill it with the average color of the target image. Now hold on to your seats, because this is the getAverageColor function. And I can probably hear you think right now, oh yeah, this looks exactly like the complex math and complex code I didn't want to look at over lunch. So it's really not that bad. Let's look at it another way. In fact, calculating the average color of an image is really not that different from calculating any other average value. You sum everything together and divide it by the number of things. So let's do this for this neon pixels image that consists of only 4 pixels. As you might know, every pixel in an image consists of 3 color values, red, green, and blue. And we can now actually take all of these red values, add them together, and divide them by the number of pixels to get the average red value, in this case 107. You can do the same thing for the green channel and the blue channel, which is going to give us the average green color value and the average blue color value, resulting in this beautiful color, which is the average color for the 4-pixel image on the left. Now that we know all this, let's get back to our scary code. We can see we're initializing an empty array, or well, it's not empty, we're initializing an array with empty R, G, and B values. And next we're looping over every row and every column, and thus every pixel in the image. And for every pixel, we're going to add its red, green, and blue value to that RGB array. After we summed all these values together, we're going to divide them by the pixel count to take the average. And this is just the average color of the image. That's all there is to it. We're returning it as a imaging pixel, which is just imaging's way to return a color as a single pixel. So, difficult but not too difficult. Well, do you ever feel like a bad programmer for Googling something? Because I really should have done that before I wrote all that code and made those slides, because yesterday I Googled this problem and the first gist that popped up was this. It's written by Paul Ferret, and well, the code's looking pretty good, so hippity hoppity, this code is now my property. And at this point I'm thinking Paul Ferret must be some kind of wizard, because he just snapped all of the existing code out of existence and he replaced it by 2 lines. He takes our image and scales it down to 1 pixel. Then, wait for it, it just returns that pixel. And this works because when scaling an image down in Imaging is smart enough to do it properly, and it will try to keep as much of the information, of the original pixel's information, into that 1 pixel. And this includes taking the average color of all those pixels and condensing it down to 1 pixel with the average color of the original image. So yeah, nice little refactor there. Step 3 was creating those random triangles. Well, this is the lazy way to do it. This is the primary school way to do it. This is literally taking 3 random points by taking a random x and y value on our canvas and returning those in an array. This results, as you can see, in usually kind of large triangles. For our algorithm, we would much prefer smaller triangles, so we can optimize them, and sort of as we optimize them, they'll grow in size. So let's get rid of 2 of these points and replace this bit of code by this. As you can see, we kept the first random point. Instead of choosing point 2 and 3 completely randomly, we're going to choose point 2 and 3 by taking a random offset in the x and the y direction from our first point. So if you look at the canvas on the right, we can see that happen in real time. The second point gets a random x offset and a random y offset, and there it is. And we'll do the same thing for the third point. Random x offset, random y offset. And now we've got 3 points that create a triangle, but only this time we control the size of the triangle. So we've got an array of 3 points that create a triangle, and we now want to draw that on top of our image. Well, this is all basic imaging stuff again. Using an imaging draw object, we can create a polygon from our 3 points. Polygon with 3 points is just a triangle. And fill it with any color, in this case green, and draw it on top of our image. And then at the end, we return the image. But that's all there is to it. It's really just basic imaging stuff again. So that was step 3 down. We've now got our 200 triangles. We can, sort of in our mind add some extra loops and conditions. But the next big step would be to compare two images using that root mean square deviation. And if you remember from before, this was probably the hardest part. Luckily, Imagix got us covered because this is all part of their native API. You can see we're creating a function to compare two images, the current image and the target image. And using Imagix's own compare image function, we can just compare the current image to the target image and request the root mean squared error metric. The root mean squared error metric. Try saying that 5 times fast. The root mean square error metric is the same thing as the root mean square deviation metric. So this is literally all there is to all that statistics stuff from before. It's perfect. Finally, we got the triangles. We've given them a score. We got our best triangle. The next step would be to mutate that triangle for a tiny bit better fit. This is for that hill climbing stuff we spoke about. So here's a mutate shape function. And as you can see, it looks a lot like that grade shape function. It's going to take an array of points in its arguments for a triangle and return the same points for a new mutated triangle. If you look at the canvas on the right there, that's our 3 points for a triangle we want to mutate. And we've chosen the red point at random. And we can now mutate this triangle by just moving that red point in a random x offset and a random y offset again, which looks like this. And these 3 points are now our new mutated triangles. Or triangle, actually, just one triangle. So those were some key points from the PHP code. Using these key points, you can, as I said, add some extra loops. You'll probably need some conditions and like a couple lines extra code. But with this key information, you should be able to recreate that algorithm. So remember how I said that the original algorithm in Go was fast? Well, turns out it's not fast at all in PHP. Actually, by the first time I wrote this 3 years ago, I pressed execute and nothing happened. So obviously I was quite frustrated and I just sort of walked away to get a coffee. And when I came back 12 minutes later, I was just about in time to see the final triangle being drawn. That's how slow it was. It took 12 minutes. So the JavaScript version of this algorithm can do it in about 2. So I'm not saying it's a competition or anything, but yeah, good goals make good progress. But first, we need to be able to measure our progress. And we'll do this using profiling tools. Here's some names that might ring some bells in no particular order. They're not all profiling tools either. Some are just like command line tools or UIs, different stuff. But the star of the show today is obviously Blackfire. Just gonna take another sip. Talking is difficult. So yeah, today, Blackfire. It's not going to be a sales pitch. You've probably just seen the previous talk about using Blackfire for tons of cool stuff. So I'm just going to show why Blackfire was a dream to use for this algorithm. They have lots of cool features you won't find in any of the other tools on the list, like it doesn't only profile CPU time or memory usage, but also I/O time, which is going to be a big one for us. Network timing, SQL queries, lots of cool stuff. Personally, I like them the most because they have the easiest to use UI. Like the first time I used this, it literally was self-explanatory. I didn't know anything about profiling. I clicked around. Sorry, some birds outside. Quickly close the window. So the first time I used them was just like self-explanatory. Yeah, I didn't know anything about profiling. Started using them. Half an hour later, I was creating profiles like crazy. So yeah, I'm just here to tell you about the first magical time I used it. Also, did I mention it's free for local use? So you can just sort of add the Blackfire CLI tool to your set of cool tools to use. And anytime you need a profile, you just use Blackfire run and generate a performance profile for free. But before we throw our generate code right at it, we'll have to make some changes. Well, as I've mentioned before, our primitive algorithm has a random component to it. This means that every time we run it, it's going to be slightly different. There's going to be slightly, different amount of triangles, slightly different amount of loops, slightly different amount of optimizations because of that hill climbing stuff. And for better or for worse, the resulting execution time is going to be slightly different. But for every XKCD comic, there is an XKCD comic that provides a solution. In this case, the solution is to get rid of the randomness, or at least some of it. We can hard-code the algorithm to only ever create 50 shapes, do 50 optimizations, and 50 loops. That way, we're sort of taking away the randomness of hill climbing. There's still the randomness in those random triangles. We were selecting random points, so there's no way we can really easily get rid of that, except by maybe doing exactly what this comic does and faking the random integer method. That's a bit out of scope. In fact, Blackfire actually has a better solution. Using the samples option, we can execute and profile our generate code not only once, but 5 times. And Blackfire will seamlessly, behind the scenes, take average values of all the profiling data it collected, which results in this beautiful thing. And the first time I saw this, I was very excited. Not necessarily because of all the profiling stuff, but because of this, the call graph. And more specifically, because of what I could see in the call graph. Because in here, we can very clearly see our entire algorithm written out in steps in a cool diagram. You can see we're adding 50 shapes. We're then finding the best step 50 times, optimizing that step 50 times, and then doing a lot of computations, computing some colors, and comparing some images. So this really blew my mind. I never told Blackfire what this code would look like, and they just sort of threw this diagram at me, which is more or less what I had on paper right next to me at that point. So apart from that, more cool stuff that you might have already seen. We can clearly see a hot path in red in our call graph leading down to the most traveled nodes. If we click on it, we can see some more detailed metrics like I/O time, memory usage, etc. We can also go to a more local version of the call graph on the right, which shows more nodes. You can easily navigate around. And the same call graph and the same hot path exists for I/O times and for CPU usage and memory usage. So if you follow down the hot path all the way down for memory usage, we can see that there's something going on with export image pixels. Specifically, it's using 99.5% of all the initialized memory in our little generate code. So let's switch back to the timing tab and take a look at that export image pixels method as well. We can clearly see the hot path running down right to it. And in this case, we can see it's taking 50% of all the execution time. So we're executing for 2 minutes and 26 seconds. Well, at least 1 minute and 15 seconds of that is doing export image pixels. On the left, you can see some more metrics. We can also see this little gray bar at the bottom, which says no callies. And this basically tells us that all this shit, all of these these 1 minute and 14 seconds and those 123 megabytes of RAM are being consumed inside of this function. It's not calling any other functions. It's all happening in here. We do see, however, that there's also only one caller. It's the getPixels method. And getPixels calls this export image pixels 25,000 times. Apart from being very stalkerish, this is a problem. So let's take a look at what getPixels looks like. Well, here's the image class, and it extends imaging. It's basically a little helper class with little helpers like getPixels. The API imaging provides for export image pixels is quite complicated, and it requires all these difficult arguments, and I never remember them, so I created a helper for it. Now, this is where those 25,000 calls come from. And judging by the high I/O times we saw and the high memory usage we saw for export image pixels, I'm just going to make an educated guess and say that export image pixels is probably reading our source file from disk every one of those 25,000 times. It's not using internal cache, and that's probably where the problem lies. So as we're using this helper everywhere in our code instead of the export image pixels directly, we can easily add a cache here. And I really wish I had this nice animation when refactoring things in real life. We can now see we've added a pixels array on our image object, and it's going to store the exported image pixels. We're using the coalesce equal operator to only fill this array if it hasn't been filled before. And then finally, we just return the image's pixels as before. So let's run Blackfire again. And now we have two reports, one from before and one for after. And we can compare those by putting them next to each other, but that would be stupid because Blackfire has this really cool compare feature with those nice animated buttons too. So we're comparing the baseline to our new cached pixels report, and this is the result, which is good news for a couple of reasons. First of all, it's filled with a blue hotspot, which in this case means time saved. And if we click on export image pixels in the call graph at the bottom there, we can see a breakdown of the differences for this method call. More specifically, we can see that export image pixels has been called 25,000 times less. Also, its I/O wait time has reduced by 100%, or it's now down to microseconds, which kind of confirms our hunch that it's reading from disk every time. And finally, you can also see like an overview for just overall time, I/O wait times, CPU time, and memory usage. So yeah, don't forget that we're now profiling our little generate script, but you can use the same kind of reporting for every change you deploy to production. So you can have these really neat reports showing you the impact of every change to your code base. Anyway, back to the algorithm. This is our latest report. And as you can see, there's a new hotspot leading down to compare images. And it's actually responsible for 50% of the execution time. Compare images is like another built-in imaging method. So I have a hunch that it's once again reading from file every execution. And if we switch to the I/O tab, we can kind of confirm that. Here's that compute compare images method again. Nothing with compute, compare images is here again. And we can see that it's using 1.5 seconds of I/O time, which is a lot for reading from a local disk. So I wasn't sure if this is actually due to the amount of times we're executing this function or because of the I/O issues. Either way, this seems like a perfect case for our pixel cache again. Sadly, the only solution here is to rewrite the entire compare images function and thus the whole root mean square deviation function from scratch. I'm going to skip that. And here's the code for it. I'm not going to bore you with the codes, but I want to point out two important things at the top there. First of all, the name is horrible. Compute difference change is a bad name, but I can't change it anymore because the slides are done. But also, we're passing a bounding box now, which will be a smaller area of computation instead of calculating the difference for the entire image canvas. And most important of all, we're using our getPixel helper, which uses the pixels cache in the underlying implementation. So let's fire up Blackfire once again and look at the report for our latest refactor. And the first thing we notice is that it's actually gotten slower, but not by much, only 5 seconds on 1 minute and 10 seconds time, so that's not too bad. But more interestingly, we can see that our compare images method has now disappeared and has been replaced by a compute difference change method, which is the one we just made. And it makes sense because we basically just swapped out the implementation for that deviation calculation. It should have been more performant, but oh well, you win some, you lose some, and maybe we can come back to this later and improve it a bit more. But first, and more importantly, we'll look at getColorValue. Because right now, we can see it show up for 25% of the overall time. So let's look through our code base. Sorry, there we go. That's that getColorValue, which is taking too much time. And if you look in our code base for occurrences of getColorValue, we usually see it in this kind of context, specifically in the context of looping over pixels. We're always using 2 for each loops and ImageX pixel iterator to loop over all columns and rows in an image. And then at the center of those loops, for every pixel, we're, for example, echoing out the red color value. Well, this is something we can easily refactor to using our pixel cache as well, because the red color value is something we're storing in cache. So that looks like this. And as you can see at the top there, we're storing the pixels for this image in another array. And then instead of calling getColorValue at the center of the loops, we're just referencing the array. Something else that might jump out is that we're no longer using this pixel variable. In fact, we're no longer using the entire pixel iterator at all. Well, this seems to be another good refactor because we're perfectly capable of writing our own two for loops, which loop over 256 rows and 256 columns, because our image size in this algorithm is set. So we can now run a final Blackfire profile and pray to the performance gods. There's me praying. And remember, we're taking 5 samples. So at an average of 1 minute per sample, this should have taken like 5 to 6 minutes. Well, imagine my surprise if this finished after just 50 seconds, with an average time of 9.9 seconds per execution. That's a 90% performance increase, which is great. So I say I'm kind of running out of time. So here's the overall optimization graph comparing the start of our algorithm to after all the refactors I did up to the latest version. You can see a couple of things. Lots of blue means lots of time saved. We're also down from 2 minutes to 7 seconds, which is a 95% increase. Memory usage is down from 120 megabytes to, can't remember, 27 or something. I/O wait time is down. This is all very exciting stuff. However, this is still relative performance. There's some overhead from using Blackfire. There's also the less randomness we introduced by sort of constraining our algorithm to 50 shapes and 50 loops, etc. So now it's time for liftoff. We're going to re-enable all randomness, bump the shapes back up to 200, and we're going to do our first real timed execution. And to keep things interesting, we're going to do it for, sort of side-by-side comparison between JavaScript on the left, Go on the right, on the top right, and then PHP on the bottom left, bottom right, sorry. As I can't click 3 buttons at the same time, we're going to have JavaScript go first, followed by Go, and there we go. They're all running now. And I don't know if you hear it, but my poor MacBook's sort of spinning up its fans, or at least it was when I was recording this video. And we can see that the Go implementation on the top right is already up to 150 shapes, almost 200, and it's just about done, while JavaScript is still stuck on shape number 14 of 200. And if you follow me on Twitter, you probably already know the outcome, because PHP is just about to finish at 22 seconds. And JavaScript is stuck at shape 27 of 200. So we're not just going to sit here awkwardly and wait for JavaScript to finish. It just took 2 minutes and 30 seconds. So here are the results. And what's really interesting for me is that these two images are the same image. Sure, they're like slightly randomized, different random triangles, but they're almost the same, which means there's no quality loss in using our faster PHP algorithm. More interestingly, though, the Go image it produced, for some reason, looks way better. Like especially, I don't know if you can see it on the screen, but like in the sky, we can really see a cool gradient of triangles sort of pointing towards the top of the rocket. So yeah, here's some takeaways, and then we're done. Slightly over time. Here's your controversial screenshots for Twitter. PHP is always faster than JavaScript, and Go is always faster than both of the above, which is a joke, by the way. But here's a real takeaway. I feel like Imagic is a bit underrated, so consider Imagic. It's really powerful. It's got a great API. It's got great documentation. It's perfect for anything graphical in PHP. But also reconsider Imagic if you have to do anything performance. Next up, iterative profiling is awesome. I had a blast just like making changes to the algorithm, profiling them, looking at the results, and repeating that until it was fast. This took 3 days in actual working time, but the result is truly there, which brings me to my last takeaway. Blackfire is awesome, not only for creating great tools and making them available for free, but also for having me on their sidetrack today. Thank you.